So, hello everybody, I'm glad to see you here, and some of you are still coming, so let us begin. And last time we stopped discussing the logistic regression, the classification problems, and we generalized this approach to multi-class problems when you have not just to say if something happens or not, but have multiple possible outcomes. And we specified a so-called one versus all approach, which basically uses the approach divide and conquer. Yes, you split this problem into three smaller problems. Each of them is specialized on detection of, let's say, green triangles, blue squares, or red crosses. This may seem like a quite simple method. However, of course, there are certain caveats, yes, and certain additional things you have to consider and do before this will actually work. So today we are going to discuss a multi-class problem and hence approach further to our understanding of other algorithms as well. So let me maybe demonstrate first where are we now considering the neural network, yes. So let's say our goal is to build a neural network. So what kind of algorithm we are already so far? So far we have a logistic regression, which is one, in a sense, a neuron with certain activation function and multiple inputs. Input 1, input 2, input 3. So this is what we already know, and the output returns a probability of yes. So like 0.5 or 0.6 or 0.75 or maybe 0.99, etc., etc. And here we add, by calculating a logistic regression, here we have this sigmoid function, yes? What we are going to do today is to say, okay, I am going to add some more classifiers, also with a sigmoid function, also its own output, which are going to use the same inputs. Let's say classifier number 2, and we had also for green triangle, right? So classifier number 3, addition, which also uses the same inputs. So in a sense now our structure starts to resemble a neural network. However, it is still not, because each of these outputs, either green triangle or blue square or red cross, are independent. Independent in a sense that when you decide if this is a red cross or not, in no way you consider other outputs. So if we speak about further development of how are we going to, so this is the topic for today, yes, that's where we are going to stop. But in future we are going to add some extra neurons, which are going to use all of this. Like so. And then that will be a neural network. So basically we make one more extra step towards the neural network, stopping at this point when we have separate classifiers, which are not a network yet, but this solely goes towards that direction. So that's what we are going to discuss today, and accordingly I will show you what kind of problems we might run into if we try to use what we learned not yesterday, but last week, yes, like splitting one problem into three smaller problems. At the first sight it might look like very simple, however, the problems will start when you will need to somehow code your data. So these are called multi-class classification problems, which are accordingly what we are going to study today and next week and week after that, because, well, it allows you to use different kind of algorithms. So examples of such multi-class classification problems are like email sorting, yes, so whether this is related to work or family, or this is basically spam, yes, like weather predictions, sunny, cloudy, rainy, snowy, handwritten digits, which is our data set, which we are going to study more closely. You will have some pictures where you will see some digit, and according to the algorithm, we'll need to correctly read this number from the picture, yes. So these are examples of such multi-class problems. And image detection, of course, obviously as well. So for these kinds of problems, we can use many other algorithms as well, not just logistic regression, not just neural networks, which we will also cover during our lectures as well. But at this point, we are going straight to the artificial networks, and then we will return to some more basic algorithms, such as naive-Bayes algorithm, decision trees, support vector machines, nearest neighbors. Well, logistic regression we have already covered. We are now extending it to work with multiple classes, and artificial neural networks is our goal for now, to understand how they exactly work. So let me remind you where we stopped last time. So basically that was, we have to split this problem of detecting squares, triangles or crosses into 3 smaller problems and make specialized classifiers for each of them. Each of these classifiers then constructs this kind of a boundary which separates all the triangles from the others. Yes, it doesn't matter at this point if others are squares or crosses. We are only interested to know if this is a triangle, yes or no, which is going to return a certain probability, like P1, or let's say maybe P triangle. Likewise, the second classifier is going to return the probability of square, and the third one is probability of the cross. Generally speaking, all of these probabilities do not necessarily have to add up to 1. So normally you understand that if this is one of these 3 possible outcomes, then normally the probabilities should add together all the way up to 1, such as, like, say, for example, if this is 0.11, so let it be 0.11, this let it be 0.15, and the green one then normally would have to be, yes, 0.74, so that together all of them are adding up to 1. However, at this point it just won't happen so, and it will be completely normal to have something like this. So let's say your probability of red cross is going to be like 0.51, probability of blue cross, blue square is going to be 0.6, and probability of the green triangle might be, let's say, 0.85, yes? So they are in total more than 1, which is normal thing because they are independent of each other. One of the reasons why we want to add an extra layer and make this a neural network is this way we will be able to actually force it to narrow down these possible outcomes into the range so that all of them together are 0. Something or adding up to 1. And this will make it easier to actually make a final decision as well, because this will force smaller probability to become even smaller, and larger will be, well, larger compared to this smaller. Yes, we will return to this when we will speak about other activation functions such as softmax and reloop, rectified linear unit, yes. But at this point, it's just worth to know that we don't necessarily have to have a total of 1 for all of these probabilities, yes. We just pick up whatever is the maximum of them, and in this situation, this is a green triangle because it has the highest probability. So, of course, it is possible that all of these will shoot as 0.9, for example, for each of them. Well, at that point, it just means that your model hasn't been trained well enough yet. Yes, so it needs more iterations to continue, maybe change some parameters, yes, to be able to get better performance, of which we'll also discuss today as well. because at certain point that is a question. How are we now recognizing which model is good and which model is bad? So first of things, in such kind of a situation, yes, in order to somehow maybe meaningfully program it and try to vectorize, would be to perform a so-called encoding procedure, or specifically one-hot encoding, when you normally have, let's say, possible outcomes listed as certain list, like red, green, or blue, and what you want to have it is replaced by ones and zeros in a corresponding column. So what we are doing now, we make, since we have three possible outcomes, three classes, yes, we make three columns, one for each class. First class, and basically it says here, is it red or not? Yes or no? Yes, so the first one was red, so we have one here, and obviously now it is not green and not blue, so we have zeros here. So this way we convert our label into a matrix of ones and zeros, with ones marking the correct class in a certain column. Yes. So this is called one-hot encoding, which is one of the first steps we are going to need to do to make this work. Because our model can only predict yes or no, 0 or 1, and it doesn't know anything about red or green or blue, nor does it honestly care, yes, about it. So for that reason we need to convert it into some format which is suitable for our model. Then, once your model has been trained, it will return probabilities, yes, for each possible data entry. Yes, so basically here you can see the correct answers, these what we call them y values, whereas here you can see our hypothesis h theta. Yes, so this is our hypothesis h theta of xi, which not necessarily is exactly 1 or exactly 0. So as you can see, as I said, it produces a list of probabilities, and amongst these probabilities for each row we find whichever is largest. So for the first row, the first column has maximum, so that means the answer is red. For the second column, second row, the second column has the maximum probability, so the answer is green, and similarly so on. Yes? So basically the idea is pretty straightforward and easy, yes? And that's how we basically make a final decision here. Now let us add some more additional parameter to overcome situations when your model will be trained too how we can say, too well, too good to be true, yes? So why is that becoming any kind of a problem? So I'm going to scroll down a little bit and let's see this kind of example, yes? So here we can see three different cases of how your model might describe data. Well, two of them are not really good, and only one of them is somewhat what we desire. Which one is in the middle? Yes, so this is a robust solution which describes your data in general well. It's not maybe as accurate as the third picture, because third picture, as you can see, goes precisely through all of the points, but that is not our goal to start with. Yes, and obviously the first picture is worst because, well, this line is completely not describing the data set well enough. Yes. Well, now, why the second picture is the best choice here, not the third one? So, with machine learning problems, the situation is that normally, well, I believe we can maybe have this as a certain board, yes. So normally what you have is certain model which you want to predict something. Yes, so you have a model here which needs some training before it will start predicting well. So you also have certain data set plus labels, so the correct answers, which then you feed to this model and use, let's say, a gradient descent method to train over this data and over these labels to make predictions. And it will learn to do so for your specified data set. The problems will start, however, when you will consider, okay, this model is good, ready to be sent to production in some kind of a system, then it will go to user, and user will have a new data. The data which this algorithm previously was not aware of, was never able to see and never consider. So then, if your model is trained too specifically to this data, which is training data, then generally it will perform much worse for this unfamiliar data. Yes, and accordingly it will say, okay, but we have trained this model and showed us, I don't know, let's say 90% accuracy, when in reality then it will start making a lot of mistakes for new data, which is not familiar to this model, just because it was, well, too detailed and too specific towards this data, just exactly as is shown in this third picture. And you can imagine this kind of a situation if, let's say, user data will happen to be, oh, we can basically add some points on top of here, yes, so like here, or maybe like here, or like here. In that case, these two accurate classifier might actually perform even worse than this one, yes, for the same points. And this one would be somewhere here. So yes, here, or let's say here, maybe this is a good point to notice, yes? So here you will have this kind of error of prediction, and here it will be much smaller. So this more generic function is much better in that situation because it allows some freedom for these points to slightly deviate from their original points. So this is called an overfitting problem, yes, and that usually happens when you train too much your algorithm, or your algorithm is too complex for too simple problem, yes, and accordingly it happens so. As you know from algebra, yes, it is possible to find a certain degree polynomial that will exactly go through with these, through all of these points with zero error, yes, because you just need to count how many points you have there, add +1, and you have a polynomial of that degree for which you will need to find coefficients by using gradient descent method, for example, like we did in linear regression. Yes, so that kind of problem is easily solvable. But will that be the best solution? No, because it will then perform much worse for new, unfamiliar data. So this is a problem of overfitting, yes? And of course, there can be situations when it's opposite, when your algorithm is too simple or you have too small amount of training time to get any meaningful result. In that case, the problem is that for underfitting data, it will perform bad for your training data. It will be both for training data bad and also bad for new data. In this situation, however, it performs exceptionally well for training data, but poorly for new data. In this situation, it will perform more or less okay for training data, but also more or less okay for new data. So this is some kind of a compromise which we need somehow to achieve. And regularization is a technique which allows you to basically have any of these outcomes for your model. So until this point we had no regularization at all, Yes, so what it meant is that it produced some solution for us which was entirely depending on how many iterations we specify, what is the learning rate alpha which we used, yes, etc., etc. But otherwise, we have no control over selecting this shape of solution. If we add regularization to this kind of problem, then we will have option to somehow address this solution, yes? So here you can see some other example, yes? Some tests run on certain microchips, so we have two tests. One is x-axis, microchip test 1, second test is y-axis, and both of these tests score in any range from -1 all the way up to, let's say, +1, yes? Well, maybe some of them will be a little bit extra 1, yes, but then again, here you can see that the model that tried to find the good details, well, you can consider maybe this is some kind of, I don't know, size of the microchip error in its size, yes, maybe it is too small or too big, yes, and we want only microchips matching the certain size, yes, which will be in a certain circle, yes, inside of this data set. So our normal area of interest would sooner look like this kind, yes, more generically. However, our algorithm did overfitting and tried to, you know, find all the possible ways around, and even made this kind of sorry, not a complete line, but here, which means in this particular case, if you will happen to see some very anomal microchip having this result, then your particular model here will say that this is a good chip. It passed both of tests. However, in reality, it's too incorrect score. Yeah? So here is this area, problematic area, that will include some of obviously bad microchips and will identify them as good ones because it was too focused on finding the best line and including as many of these crosses. So here you can see it included it. Here it could not exactly include it, but was very hard trying to do so. Yes, here as well, and as well. Here this one includes. So basically it missed 1, 2, 3 crosses, yes, out of all of them. So, of course, it was good enough for this specific data set, but when you specify some new details which are not pictured here, it will show much worse results. So let's say we have certain probability of correctly identifying the microchip as passing the test or not. So for this training data, which you can see on the screen, the probability of correctly doing the identification was 0.83. Yes, so 83% of microchips were properly predicted to pass or not pass the test. However, then we take another box of new microchips which were not used during this training process and run this test for them. And for this new batch of microchips, the probability, or we can say accuracy, of prediction was only 0.62, which is much worse than it was for this original data. So there are multiple ways how we can fight with that. One of them is to split your data set into 2 parts. One of them is called training data set, which you will use for training, and another is a testing data set. So why do we need to do that? Well, as I was explaining right now, yes, normally you train some algorithm, then you send it into working, doing whatever it is supposed to do, and it starts working with new data. However, before actually sending it to the customer, we can say, yes, you need to verify how well it works with new unfamiliar data. And to do so, you will have to gather this data somewhere. Yes? So to avoid this kind of unnecessary hassle, yes, we can say, okay, I have already a lot of data, so I'm going to hold on to small 20% part of this data, hide it away from the algorithm, and then use it later, after I have trained the model. So this way, the testing data is hidden from the algorithm. It never sees this testing data, but you still have it, and can run the test afterwards, yes? So idea is pretty simple as that, so that you don't have to go somewhere and gather new data just to run some tests for the model that you have trained. You already have data, you just say, okay, this data will be used for training, this data will be used for testing. We can go in further and say that we want to use some of this testing data as a validation data, which we'll discuss further as well. But at this point, the idea is pretty simple, and it will help you to actually then achieve these accuracy scores. So we'll speak what is exactly this accuracy, but the idea is obviously pretty simple. It's probability of correctly identifying the case, yes? So what do we do then if your algorithm is just working like so? Yes, you can't really change much there. Maybe you can give it less time, but no guarantee that it will run any better solution, because if you give it less time, it might become underfitting, yes, and have bad accuracy for training and testing, both of them. So the solution is to use this regularization, yes? And we obtain this kind of data by using this nonlinear regression, yes, when we have as input x1 and x2, these are literally our only inputs, yes, this is x1, this is x2, but the shape is too complex to be a linear function. That happens because we have created artificially extra parameters. So we take the x1 and square it, we take x2 and square it, we make a combination of x1 and x2, so that is the data we produce ourselves to have more complex shape of the line, presumably to separate these two classes better on this plane, yes? And now we are going to add some regularization procedure with certain parameter called lambda, which then affects you how strong is this regularization. So if we overdo it with regularization, which is the second picture, you can see that then it will find the area of generic shape, but it will be not in precise place. So that will result in having bad accuracy, both for training data and for testing data. Now, if you find the correct regularization parameter, in this particular example it is 1, then you will see that you were actually able to achieve the same accuracy for testing data as was for training data. Whereas without regularization at all, the testing data was having 0.62 and training was having 0.83. Yeah? So this is without regularization. This is with a well, optimal regularization, we can say so, and this is with too excess regularization, leading to underfitting problem. So now we have this parameter lambda, just like alpha parameter before, which we can change and get this regularization controlled, yes? So how exactly this regularization is then working? In a sense, it's basically doing similar stuff as to exclude certain columns, yes? So basically, we could have achieved the same effect as the regularization does by simply striking out, let's say, this column, or maybe, I don't know, this as well, and so on, and so on. Yes? This is, well, in truth, one of the regularization approaches which later on in neural networks will be used. So in neural networks, we also can use regularization by simply disconnecting certain neurons. Yes? So we have some neurons, yes, a neural network of a sense, some connections in between these neurons, and say normally neural network has all connections for all neurons, yes, but we can intentionally cut off certain neuron links, yes, and according to that will be a regularization in neural network. But it's, as you imagine, includes too much of a handwork, because you need to then say, okay, I'm going to switch out this column and see how well it works. Well, I don't like this, okay, I put back this column and I switch out another column. We'd like somewhat more automated solution. Another example of this kind of problem is specifically including the formulas from NDNG course, yes. of logistic regression when we want to separate these two classes. Yes, here in the first picture we make a straight line which formula is theta 0, theta 1 x1, theta 2 x2. So this is a linear function, and as of such it looks like a straight line. Yes, which is overall not so good boundary between these two classes for this specific problem. Yes. The second picture is much more accurate, but it's not too accurate as the third picture, yes? So it still has some errors available, like here, including these crosses, which this picture does not. And the function for it is theta 0, theta 1 x1, theta 2 x2, theta 3 x1 square, theta 4 x2 square, theta 5 x1 multiplied by x2. So this is the formula for this kind of line. As you can see, it includes more inputs, more features, which we can generate artificially. The final line, third line, is very accurate. It actually is 100% accurate because it separates precisely each of these circles from each of these crosses. It does not include any cross in the region selected, but as you imagine, it is too specific for this data set, yes? And when you take any other new data set, which will not look like this, but it will still have somewhat common to this shape, yes, it will start producing errors, and probably even more errors than the second picture would. So that is the reason why we want to avoid this overfitting, yes, and this is an underfitting. So how we can do it? As I mentioned, you can strike out the columns, because obviously these pictures are different only in the sense that this second picture has extra these parameters, and this third picture has additionally extra more parameters than the second one. So if you cancel out these unnecessary parameters, you are going to revert to the second picture from the third picture, and even maybe to the first picture if you cancel out all of them and just leave theta 1 x1, theta 2 x2. Yes, so striking out the dataset columns is one of the solutions, which also usually happens if you have more data than actually is necessary to describe your problem. Yes, like too complex. So let's say we are speaking about selling the houses, and in addition to area, maybe age and something else, we start including somewhat, I don't know, weather factors, maybe, yes, maybe political situations, maybe some kind of nuclear plant constructions nearby, etc., etc. Just too much of the inputs to consider for the simple price of house, which may be important, maybe not, but then it becomes too complex problem for this algorithm, and you need to choose another algorithm to address it properly. So one of the options is to reduce number of the inputs to make this problem kind of simpler, yes, because not necessarily always we really need to have all the possible information about our object. Yes, there is this so-called Pareto law, which describes that for 80% of situations for these scenarios, yes, you are required to have only 20% of the model parameters, and other 80% of model parameters are excess, yes, too much. Then again, we can use this regularization technique, which I described today. We keep all of these features, but then what we do here is add extra multiplier here. So say, now we are going to say that it's going to have extra A1 multiplied to this, extra A2 multiplied to this, etc., etc. So certain weights, which will then give certain priority to our columns of data, and we do not assign them automatically. That is one also thing, and it works particularly nice if the features, well, you can't simply throw out any columns. All of them are necessary for this kind of problem, yes, but it also overperforms for your training data set. So how are we supposed to add this regularization? This regularization can be actually added to linear regression, to logistic regression, to neural networks, to any kind of algorithm. All you need to do is to include an extra to your cost function. So let's say here we have a cost function of our logistic regression, which looks like this, as we have found out last lecture. And what we do here is we now add extra regularization, like so. So now, in addition to normal cost, which is related to accuracy, how accurately it will predict, we want to say, okay, I want to minimize as much as possible parameters theta 3 and theta 7. Smaller, and theta 7 also smaller. For example, only these two parameters, yes, because I have found out that they actually contribute too much to this irregular shape. Also, at the same time, I want to have certain, how you could say, setting, yes, parameter, which will allow me to say how much attention should be paid to this theta 3 and theta 7 parameters. So let's say if I specify 1000 here, then it will force the algorithm to minimize them much more than if I specify 1, yes? Because this is a cost function, and the cost function is going to be minimized. That is how gradient descent works. It only cares about making this j as small as possible. And now you have added extra condition here that theta 3 and theta 7 are multiplied by 1000, so this adds extra to your cost function, and it will then start considering what is more important, this part or this part, yes? So lambda choice really matters, and we will have in our practical exercises opportunity to change this. Well, you basically already have seen this from the pictures, yes? So here we have different lambda values. Lambda equal 1 and lambda equal 25. And here we have lambda equal to 0, yes? So it will actually affect shape and total accuracy of the algorithm. Other than that, there is not really much to eat. And honestly, we are not even going to separate certain columns. We are going to actually include all of them. The first column, the second column, the third column, and multiply them by equal number. So at this point, we make certain priority, like somewhat like third and seventh columns are somewhat special, yes? Which is mostly not true, which is mostly what we don't want. However, we still want to somehow control all of thetas. Theta 0, theta 0 not exactly, because it's for bias, it's not for data, yes? So that means theta 1 all the way up to last theta what we have. So we want all of them multiplied by this. And notice also here that we take squares, because theta can also be negative number. This is one of the tricks the algorithm might come up. So it will say, okay, I need to make this cost function as small as possible. So if you would not have these squares, then it would say, okay, I'm going to take theta 3 and theta 7 negative. That will reduce cost function. So to avoid that, we make them square, so they are always positive. Yes? Also, well, not necessarily they are always positive, they can be negative, but their contribution to cost function will always be positive, yes, this way. Also, squaring small numbers makes them even smaller, yes? So if we have 0.1, 0.1 squared is 0.01, yes? So it will then prefer them to be smaller rather than larger. And if we do that for all theta parameters, yes, then we can write this as this kind of a formula where you have this lambda and this as 2m parameter, yes. So basically what is important to note here is that my numbering for I starts from 1, which means theta 0 is not included in this sum, yes, it doesn't participate. Because theta 0 is responsible for bias, this column of 1s we are adding to our data set at the beginning. And this is not a data. Moreover, it will be the same for all data sets, yes, it will always be a column of 1s. So for that reason, we do not want to regularize theta 0, and we want to exclude it. So hence, this formula will be like theta 1 square plus theta 2 square, etc. No theta 0. Yes, we don't regularize theta 0. Which again can be done in vector form,
because here we have square, yes, and then square and summation of all these squares, yes, can be done as a theta multiplied by theta transpose, and then divided by multiplied by lambda and divided by 2m. So vectorized form is also quite simple here to do, not big problem. However, now you need to remember that our gradient descent uses derivative of cost function, and if you add something to the cost function, then something will appear also in a derivative as well. So for that reason we need to consider that too, yes? Well, thankfully, to calculate this derivative is pretty straightforward and trivial, and this is again the case when we you might ask why we have 2 here, 2m. Well, m comes from this one, yes, so we basically had this inside of this summation, and then we split this one sum into these 2 sums, so this m carries over. Lambda was regularization parameter which has to be there, so the question is where these 2 came from. Well, it was again a little bit of cheating for our convenience, because we know that when we calculate derivative, it's going to produce extra 2 here, which later on we will be able to cancel out. So this was a step ahead thinking, yes, knowing that I will have extra 2 there, so that in derivative it goes away, I include these 2. Because at this point it doesn't really matter if you use lambda of 1000 or 500 or 2000, yes, it just scales towards to your lambda parameters, yes. So the derivative then for this summation is summation of theta without square and without these 2, yes. So in the cost function then we write it like lambda versus 2m summation n I from 1 theta I square, that is for cost function, and that is for the gradient. Well, otherwise they are very similar. Now the question is, how are we supposed to vectorize these, knowing that we don't want to do anything with theta 0? So normally you have a vector of theta parameters which includes theta 0, theta 1, theta 2, theta 3, etc., etc. And we only want to do this regularization for this part of a vector, not all of this vector, yes? So we might as well point out for this kind of problem while we are at it, and do it like this. We are going to multiply this almost identity matrix, yes, except that first position is 0, with the theta column, which is going to produce theta column, because identity matrix does not change a matrix. Well, except that it's going to nullify this theta 0 after you multiply these 2 matrices. Yes? So the goal is achieved. Then you multiply this theta column with 0 first element with this row by column, produces this sum of squares, yes, which is what we wanted to get. Yes? So this part is quite simple to vectorize. You simply, in addition to regular theta vector multiplied by theta row multiplied by theta column, in between add this identity matrix where you have intentionally nullified the first element, yes? Because normal identity matrix would have 1 here as well. That is the identity matrix. Well, because you have nullified this first column, it's going to nullify this theta 0 and this theta 0, so it will not participate in calculation of the sum of squares, which is what we wanted to do. So not as difficult to do as you imagined. It will, in Python, it will just add extra line of code that in your j, which you have already calculated, you will have j plus something like numpy dot, yes, of these theta vectors. Well, I'm going to mark it like this. Then some kind of a identity matrix A, and then again numpy dot with the remaining theta transpose. Yes, so basically it will include 1 extra line of code, which is fine. As also considering that we write a custom function for the cost function and gradient descent, it will be inside of that cost function, and accordingly you won't even feel it. Yes. Now, for the derivative. For the derivative, it works exactly the same, except that we don't have to multiply with the row to get squares, because we no longer need these squares. Yes. And also, we want to add them together. So multiplying with this identity matrix is not exactly going to add them all together, but wait, no, it actually is. Not really sure about this part. We'll see more in details in practical exercise with example, yes, but as far as I understand, this is also going to be a single number, yes, once you multiply this matrix with this column vector. Or not? No, it shouldn't be, because identity matrix keeps the matrix, so that's the idea of identity matrix. So we need extra step to add these remaining vectors together, which slide is missing for some reason. Okay, we'll return to this in practical exercise, because right now I'm a little bit confused myself why there is something missing. But something is really missing, yes? So I will try to find it, add extra slide, and we'll return to it when we will have a practical exercise to say, okay, that was the problem, this part was missing. Because as I see right now, it is not going to calculate this summation. Yes? It's just going to nullify the first component of this theta vector, and that's it. Yes? So how are we supposed to further add this summation? Not exactly clear at this point. Well, of course, we can run the function sum in Python. This is always going to work, but it's not a probably vectorized solution like sum of theta, yes, which will work. But well, we'll see what kind of smart code would look like in this situation in practical exercise. So okay, and the final for today, yes, topic would be the performance metrics, yes. So for the logistic or linear regression, we kind of understand if your solution is good or not when you try to predict the price of house and it says your predicted house is too different from the actual price. Here also, when you try to classify a picture of cat or dog, it's quite clear that it works correctly or not, but then we cannot really say in general how well the algorithm is working. So for that kind, we need certain metric that will tell you that, well, the accuracy of your algorithm is, let's say, 90%. So that means that out of 1,000 pictures, on average, it will identify correctly 900 of pictures and 100 incorrectly. Yes? So these kind of metrics are not the only one, yes, so there are many different metrics, but today we'll start with the most simple one called the accuracy, which defines this classifier in general. I will also point out why exactly this might be not the best solution for all situations, yes, but let's say we have, I don't know what this could be. Let's say this would be some COVID test results, yes. So we have some people who are really having COVID and some people who were falsely found as positive for COVID test, and some people vice versa who were having COVID but were not found out because it was false negative. Yes. So we can summarize all of these cases in a matrix called a confusion matrix. So this is a confusion matrix which puts all these possible outcomes together. When first you have COVID and you were identified having COVID, you don't have COVID and you were identified like not having COVID, you don't have COVID but you were falsely identified that you do, and you don't have and you do have COVID, no, vice versa. I don't remember whichever I mentioned, but there are four possible outcomes, yes. And the correct answers are situated on this diagonal of the confusion matrix, like here. So when positive and positive match and negative match. So here we have prediction of our algorithm. Here we have what was actually true, yes? And then we can have two cases when it's making an error. Either it is making a false negative, when in truth it was positive, but it predicted as negative, or it is making a false positive, when it in truth was negative, but was predicted as positive, yes? So these are kinds of errors. And the benefit of confusion matrix is that it shows you all of this information. You can actually have detailed analysis, how many pictures of cats were incorrectly identified as dogs, and vice versa, how many pictures were not identified, etc., etc. Whereas accuracy, well, accuracy is going to say you in general that 90% of pictures were identified properly, and no other information at all, yes, which sometimes is not good enough. Yes, let me show you an example of this kind of a situation. So consider we have some network security company, yes, running some protection software in networks, yes, and what they do is they analyze traffic, computer network traffic on different parameters like IP addresses, port numbers, I don't know, protocols, etc., etc., destination address, source address, all that stuff, yes? And then their task is to say if there is some kind of security breach happening at the moment, yes? So, as you understand, our normal traffic for majority of time will be non-critical, non-breach. So this is some kind of a normal traffic. And only here and then some breach will happen, and then again we are back to normal traffic. So the security breach is rather rare event. So if we kind of make this type of confusion matrix, yes, for, let's say, you have transmitted, well, for simplicity, let's say 1,000 of packets. Out of these 1,000 packets, let's say 2 of them were malicious. So hackers attacked packets, yes? Now we have a confusion matrix saying how many of the packets were identified correctly as secure. So that means, let's say, I don't know, let's pick some number. Let's say 900 of all packets were actually identified as normal packets. Also, it was not able to find any of these malicious packets. So we have 0 here. So it did not find any attacks. In truth, there were attacks, but it didn't find any. And accordingly, then we have to split the remaining parts. So since it didn't find any attacks, that means when it was actually true that it was malicious, it returned a negative, yes? So that brings us here, which is 2, and the remaining part goes to 98. So just wait a moment. No, it's opposite. It's opposite. Sorry, because the true class is on x-axis, which means true class was positive. That's correct, and the predicted was as negative. No, it was correct. So what we can see from this is that the accuracy of prediction is 90%. However, with this, it was not able to detect any kind of intrusion. So although it seems like a high number, it doesn't really work because it doesn't pay attention to these very rare events. So in that sense, accuracy is much, much worse. Or maybe another example, which will be more clear. Let's say you have pictures of cats and pictures of dogs. In your dataset, you have, I don't know, let's say 999 pictures of cats and only 1 picture of dog. So even if it incorrectly identifies dog's picture as a cat, it still is going to achieve accuracy of 99.9%, which is exceptional, remarkable accuracy. But The problem is that the algorithm in that situation is going to work like this. So you insert a picture, then it says a cat. It doesn't even have any logic, any calculations, any whatsoever. It's like in pseudocode would look like if any picture, then cat. Yes, it's not even going to bother trying to predict is it a cat or dog because it automatically achieves accuracy of 99.9% for this data set, which is very bad for us. So we'll speak also about other performance metrics where it will matter and where you will actually see that it does poorly. But at this point, considering that we are going to work with a data set of equal amount, so that is balanced data set, that is not going to be a problem for us. So that is quite important, that our data set at this point is balanced. What that means is if you have pictures of cats and dogs, you are going to have more or less equal amount of them, let's say 500 of dogs and 500 of cats. In that case, accuracy actually works pretty well. But for problems where you need to find very rare events, like, I don't know, some signal from space, radiation, or some hacker attack in a computer network, or maybe some rare genetic something, yes, which happens very rarely. Accordingly, in those situations, accuracy is not the best solution. Yes, so that is why I wanted to mention it so far. Now, for the confusion matrix, when we have a binary case, yes or no, this confusion matrix has only 2 rows and 2 columns, but we can extend this to having more than 2 possible outcomes. Let's say handwritten digits from 0 to 9, yes, and then you will have 10 rows and 10 columns, which will then, again, on diagonal show you correctly. So let's see here, for example, this is actual of one of our future practical exercises, yes, when you will have these kinds of pictures and you will train a neural network to read this number. And as you can see, in the end, you are going to get quite good results because on average, I believe we have around 1,000 of each of these numbers. So 100, so 0, 1,000 of ones, 1,000 of twos, and so on and so on. And then you will be able to see how many of zeros were identified as zeros, which is this number, how many ones were identified as ones, which is this number, etc., etc. And also, you will see any other possible incorrect classification. So in this case, this confusion matrix allows you to answer a very simple question. For this kind of a problem, what is the most common type of error? Which 2 digits it misinterprets most often? So you are going to see the maximum numbers you can find here, which in this case is 13, yes? And 13 is situation when you have number 2 misinterpreted as number 7. So this gives here 13 and also vice versa. And here as well, yes, 7 and 2. So in total that is 19 mistakes, 13, when you have 7 and predict 2, and 6 when you have 2 and predict 7. Yes, because this is the same kind of mistake, but so that is the most common type of error. Again, however, we also have this kind of mistake when you have 9 and predict it as 13. Yes, so as 7, sorry. So here you can have detailed analysis of what exactly is happening incorrectly. And in that sense, if you have calculated this confusion matrix, and in Python you can simply call a function called confusion matrix, and it will produce this confusion matrix for you. To calculate the accuracy, then you need to have the correct predictions, which are true positive and true negative. That is, when it was positive, it predicted as positive correctly, and when it was negative, it also predicted negative correctly. So this is the how we say in probability set of events that satisfy our condition, and the total amount of events that are possible is including mistake detected situation. Yes, so this ratio is then, in a sense, probability to make a correct prediction which is called accuracy, yes? So that accuracy can and we will use to actually verify. So from today then, we know multiple things, yes, such as, which we can put together, yes? First of all, in order to be able to say something about how well it performs on familiar and unfamiliar data sets, you need to split data into training and testing data, for which you will be able to measure this accuracy, and it will be generally different numbers. So accuracy for training data does not necessarily will be the same as for testing data, which you can then address with a regularization, as you can see here, to force in either way to decrease the training data accuracy without achieving good testing accuracy, or to improve the testing accuracy, maybe at some expense of training accuracy, yes? And then finally, you can this way avoid this regularization problem. So, to conclude today's lecture then, with this accuracy, what we are going to go further is the neural network, which will, as I mentioned, have one extra layer at the end with all connected neurons. So specifically, right now, where we are at, at this point. The next step will be adding one more extra layer of neurons, but before that, we will also consider how are we supposed to describe these hypotheses. Yes, because these are three hypotheses. This is hypothesis H1, which has its own theta parameters, theta 0, theta 1, theta 2. This is hypothesis H2, which also has its own parameters. And this is hypothesis H3, which also has its own set of theta parameters. So basically, what we are going to do is to repeat this procedure 3 times to train 3 different hypotheses. But there is a way to actually put them into something called a theta matrix, which will then have not just rows, but also columns, where each row is going to be one hypothesis in this theta matrix. But that is next time, yes? So for today, what I wanted to tell you was that. Also, I wanted to, because some of you were asking some questions, I wanted to show you some examples how reports should look like. So I will show you 2 examples. This, in fact, was not your practical exercise, so to get a good report, you don't really have to do much. You have to say what is the task you are doing and show the results. Even this code is not really necessary. Yes, you can skip this code. That doesn't really is necessary. Just be sure to include any output, such as text, yes, which is the maybe some kind of prediction, or pictures. Then here you describe that you calculate the cost function, you specify difference, yes, etc. So basically the task, results, and etc. So this is good enough for me to, well, I consider this actually good and nice report, especially considering our formatting, and